The last problem is a differential equation. Here we're solving the second order differential equation with linear coefficients, and it's an initial value problem where this equation is equal to f of t, where f of t is defined by this graph. So notice here I have a piecewise defined graph. I'll define it up here. And this graph has three different definitions. We have 0 from t goes from 0 to 3. I'll put that in my definition. 0 as t goes from 0 to 3. And then we have this line that goes from the point 3, 0 to the point 5, 4. And we have that line from t equals 3 to t equals 5. 3 less than or equal to t is less than 5. And then when t is greater than 5, we've got this horizontal line. We get 4. This is every point on this line has a y value of 4. So I need the equation for this line. I'm going to use y equals mx, but in place of x we have t plus b, the slope-intercept form of the line, where to get the slope I'm going to use my rise. Here I'm going up from 0 to 4. I have a rise of 4, and my run going from 3 to 5 is 2. So my rise over run is 4 over 2, or 2. My slope is 2. And I need my y-intercept. I can find the y-intercept by using either one of these points on the line and substituting in. I'll use the point 3, 0. When t is 3, y is 0. That gives me 0 equals 2 times 3 plus b. This is 6. Bring the 6 over and we get negative 6 is equal to b. So the equation for this line is y equals 2t minus 6. This is f of t written as a piecewise defined function, and then writing f of t in terms of unit step functions, I'll do that over here. I'll rewrite the entire equation. I get the second derivative of y plus y is equal to, notice that I'm starting with 0. I don't really have to put that 0 there, but I'm going to. And then I'm adding on 2t minus 6. And I'm going to multiply that by my unit step function that acts like an on-off switch. When t equals 3, this part gets turned on. And then at 5 units, when t is equal to 5, I want to get rid of this 2t minus 6. So I'm going to subtract off 2t minus 6. So I'll take away the 2t and add 6 to cancel this out. And then add on the 4 that I need, plus 4. And that gets turned on at when t is equal to 5. So multiply it by the unit step function ut minus 5. So this problem is made to work out very nicely for you. I'm going to simplify this just a little bit. And notice that this 2t minus 6, you could factor out the 2 and that leaves you with a factor of t minus 3. So here I have a t minus 3 multiplied by my unit step function with that same shift, ut minus 3. And here I've got negative 2t plus 10. If I factor out a negative 2, that'll leave me with a t minus 5. Notice that's multiplied by my unit step function with the same shift. So now to solve using Laplace transforms, I'm going to apply the Laplace to each term, and the Laplace of my second derivative is given down here, is s squared y minus s y of 0 minus y prime of 0. Then I have plus y. The Laplace of y is capital Y, and then is equal to, here when I do the Laplace of 2 times t minus 3 u to the t minus 3, this Laplace of the u t minus 3 is going to give me an e to the negative 3s times the Laplace of 2t. And the Laplace of 2t, because remember that shift is taken into account by this exponential function, is the same as 2 times the Laplace of t, where the Laplace of t is right here, 1 over s squared. So I get 2 over s squared. Okay, and then I have minus. This Laplace of the unit step function is going to give me an e to the negative 5s. And then here again I have the Laplace of 2t, which is 2 over s squared, times 2 over s squared. Okay, let me go back and fill in my initial values. My initial values here tell me that y of 0 is 0 and y prime of 0 is 0. And so both of these terms drop out. And then my terms on the left side are left, I'm left in terms of y. I have s squared plus 1 times y equals my terms on the right side. E to the negative 3s times 2 over s squared minus e to the negative 5s times 2 over s squared. To solve for y, I'm going to divide by s squared plus 1, and that's going to put an s squared plus 1 in each one of these denominators. So our next step is going to be to apply the inverse Laplace. And when we apply the inverse Laplace to y, we get y of t. And then applying the inverse Laplace to each one of these terms, to do the inverse Laplace of 2 over s squared plus 1, I'll need to do partial fraction decomposition. And the nice thing is that the second fraction is identical. So whatever I get here, the second fraction will look very similar. So using partial fraction decomposition, I've got 2 over s squared times s squared plus 1 is equal to a over s plus b over s squared plus cs plus d over s squared plus 1. If I multiply each term by the common denominator, I get 2 is equal to as times s squared plus 1 plus b times s squared plus 1 plus cs plus d times s squared. I can expand this to get as to the third plus as plus bs squared plus b plus cs to the third plus ds squared. And then equating coefficients, I only have one constant term, so I'll start there. With my constant term, I get b is equal to 2. Then I'll go to my s term, and I only have one s term, a, and that's going to be equal to 0. And then for my s squared term, I've got b plus d is equal to 0. b is 2, and so d has to be negative 2. 2 minus 2 equals 0. d is negative 2. And for my s to the third term, I get 0 is equal to a plus c, where a is 0, so that tells me that c is 0. Okay, so if I take just this part and write it in partial fraction decomposition, I have it up here. See, a is 0, so this term drops out. b is 2, it becomes a 2. c is 0, this part drops out. And d is negative 2. I'm going to get inverse Laplace of e to the negative 3s times 2 over s squared minus 2 over s squared plus 1. Then I get minus e to the negative 5s multiplied by this same difference in fractions. 2 over s squared minus 2 over s squared plus 1. Okay, so when I do the inverse Laplace, for here I'll get, this tells me I have a unit step function, and I've got a shift of 3 units, u t minus 3, and it tells me wherever I have a t in these inverses, I'll have to have that same shift. So 2 over s squared, I know that the inverse Laplace of 1 over s squared is t. That 2 comes out and it gives me 2t with that same shift. So I have 2 times t minus 3. Then here I have 2 over s squared plus 1. Again, that 2 can come out, and the inverse Laplace of 1 over s squared plus 1 is sine 1t. If b is 1, then this becomes 1 over s squared plus 1, and this becomes sine 1t. So I get 2 sine t, where that t has that same shift, t minus 3. Then I have minus my unit step function, this time with a shift of 5, times, because I have the same thing in brackets here as I did over here, I'm going to get the same result, but this time my shift will be 5 units instead of 3. So the only thing that will change is that this becomes t minus 5 instead of t minus 3 in both cases. And here's my solution.